Hello everyone, my name is Wenqi, and today I'm going to be telling you about my thesis work concerning Stein-Weiss inequalities for cancelling L1 data. This talk is going to be part of the Happy Hello World series of talks, and in particular, I'd like to thank the organizers for giving us this platform to share our work on. So for those who don't know me, I'm a PhD student at the Australian National University. My thesis advisor is Lam Yung, and I'm going to be on the job market looking for a job starting in 2026. So before I begin with my talk, I got to show you my disappearing trick. So now that I'm out of the way, I am going to start by defining the key item that we're going to study, and that's going to be the Riesz potential. So we're going to study the Riesz potential in Euclidean space in dimensions 2 and bigger. So let me define this Riesz potential for you. So for a lambda strictly less than the dimension but bigger than 0, I'm going to define the Riesz potential denoted by I lambda f by this convolution formula. So it's going to be a convolution between f and this kernel x minus y to some negative power n minus lambda. So let me just clarify. The reason why we are interested in formulas like this is because they have a special property with negative powers of the Laplacian. So for them to be exactly equal to a negative power of the Laplacian, I'm going to need some constant which depends on n and lambda. So I'm just going to tell you now that I'm going to ignore these constants just to make the presentation a bit cleaner. One other thing I want to point out about this formula is that it makes sense for a vector valued f. And what do I mean by that is I just mean evaluate this convolution for each component of f. So we can define the vector I lambda of f by just convolving each component. One more thing I'd like to clarify is that because I'm ignoring these constants, I may as well ignore constants everywhere. So I should just tell you that I'm going to use the Vinogradov notation, a less than squiggly line b, to just denote that a is bounded above by b up to some positive multiplicative constant, which is going to depend on the quantities from the theorems that I'm specifying. So now let me ask the main question of my work. And that's going to be, for what functions f in L1 with this power weight x to the a, is I lambda of f going to be an LQ function with this power weight x to the b? So let me just give a bit of motivation for this question. Before I do that, let me just state this as an inequality. So I'm just going to ask for this inequality with some finite constant. So why might we be interested in this inequality? Well, that's because it corresponds to a Sobolev inequality. So 2 implies a Sobolev inequality, and it's a four-line argument, so I might as well just show you. So the four-line argument goes something like this. So if I have a continuous, compactly supported function u, and I take the Green's function or fundamental solution for the gradient, I can write u using this convolution formula. So if you've done anything with these Green's functions before, you'll know that this Green's function is going to have the same homogeneity as I1. So what we do is we just do triangle inequality to bring the norm inside the integral. And when we do that and drop our constants, we can relate this Green's function g with I1. So this just gives us a pointwise inequality between u and I1 applied to the norm of the gradient. So now what happens if I take this pointwise inequality corresponding to 4 and I assume a Stein-Weiss inequality corresponding to 2? Well, if I combine these two, I'm going to get the following estimate. So this first line here is just this pointwise inequality, and then this second line is just going to be me applying the Stein-Weiss inequality to a function f is equal to the norm of the gradient of u. So what we arrive at is this Sobolev inequality for the gradient of u in L1 and u of x in LQ. So you may sit there and wonder, why am I interested in this problem? I mean, we know a lot about Sobolev inequalities. In fact, we know so much about them, you can look them up on Wikipedia, right? So let me say a little bit more about this. So note here that the previous argument is also going to work with functions f is equal to the norm of AD of u for some elliptic differential operator A of d. So this is precisely the operators that satisfy this Green's function representation. So here, g is going to be the Green's function for A of d. And what I'm saying here is that you can always represent u by a convolution between a Green's function and an elliptic differential operator. So when you have this representation, the argument on the previous slide proves this Sobolev inequality. So why is this Sobolev inequality interesting? It's interesting because of this L1 endpoint. So let me say a word about that. I want to point out that at this L1 endpoint, there are going to be no useful inequalities of this form. So this is a result known as Ornstein's non-inequality. And what I'm saying here is that there's no non-trivial inequalities between a first-order elliptic differential operator A of D and the gradient. So in particular, the L1 Hardy-Sobolev inequalities are going to be really important because they're a replacement for the failure of these L1 inequalities. So because we don't have these L1 inequalities, we need these inequalities as a replacement for them. So let me just confirm that if I'm in LP spaces for p strictly bigger than 1, I don't need to do any of this. So what I'm saying is if I have an LP with p strictly bigger than 1, these inequalities are known as Calder and Zygmund inequalities, and so we don't need to do the analysis that I'm going to show you. So hopefully now we're motivated to study the Sobolev inequalities. So let's begin our analysis. The first step of our analysis is that I want to study some of the necessary conditions to these inequalities. So the first condition shouldn't be too surprising. It's just that b is bigger than minus n, and that's just to guarantee local integrability of this weight. The second condition is just going to be that q can't be too large, and that's just going to relate to the Sobolev inequality. And the last necessary condition is going to be the scaling condition. And what that comes from is that it comes from that this inequality is scale invariant. So if I rescale f and I compare the resulting parameters on the right-hand side and on the left-hand side, I should arrive at this exact equality between my parameters b, q, a, and lambda. So I just wanted to highlight these conditions because I'm going to be referring back to these conditions as the necessary conditions throughout this talk. And the reason why I'm doing this is it's just to tidy up my theorem statements so that you can see which assumptions I'm placing in addition. So let me just help you visualize these conditions. So I'm just going to recall the same three conditions, but I'm just going to express the scaling condition in this slope intercept form. And that's going to give us the following graph in AB space. So these necessary conditions essentially just draw out this triangle in AB space. So in particular, if I oppose additional constraints on A, so for instance, if I in addition require that A is negative, I'm essentially then restricting to this subtriangle here. And my goal is essentially to see how much of this triangle I can prove a Stein-Weiss inequality for. So let's address that goal. The easy starting point is to address what happens when A is negative, first of all. So when A is negative, we can prove the Stein-Weiss inequalities for every f in L1 with this power weight. So let me just recall for you the famous Stein-Weiss theorem. So I just need one sentence to tell you that my parameters satisfy the necessary conditions. Then I'm going to additionally suppose that A is negative, and then we can prove the Stein-Weiss inequality for every f. So this is all well and good. Now I want to ask the question of what happens when A is non-negative. So unfortunately, something goes wrong. So let me tell you about what goes wrong in this regime. So the problem is that you can approximate delta functions at the origin when you have an L1 space with some positive power weight. So why is this a bad function to approximate? This is a bad function to approximate because if you compute I lambda of delta naught, this is never going to be an LQ function for any Q or power weight exponent B. So why is this interesting? Well, I just want to point out that this barrier, so let's say this counterexample, doesn't occur for Hardy-Sobolev inequalities involving gradients. So in particular, you can prove a Hardy-Sobolev inequality in this range, even though you can't prove a Stein-Weiss inequality in this range. So let's explore why this occurs. So one reason is that perhaps our earlier approach missed certain structural considerations. So let me recall our earlier approach, because I imagine you've probably forgotten. It's just this two-line argument that was first this pointwise inequality between u and I1 applied to the norm of the gradient. And then the second line was just the Stein-Weiss inequality applied to the norm of the gradient of u. So let me just summarize that for you. So we first had a pointwise inequality and a triangle inequality. Then we applied the Stein-Weiss inequality to functions f of this very particular form. Now, the problem with this is that both steps are inefficient, but in particular, this last step, this is not going to detect certain structural properties of f. So what do I mean by structural properties? One thing I can mean is that the difference between the gradient of u and the norm of the gradient of u is that the gradient of u is going to be a curl-free vector field, but it doesn't make sense to consider the curl of the norm of the gradient. So that's one structural property that I'm missing. Another structural property I'm missing is that the integral of the gradient of u for a compactly supported function u, this is going to be 0. However, the integral for the norm of a gradient of u is non-zero. So here are two properties that I'm missing by taking the norm of the gradient. So now I might want to ask, can I prove a Stein-Weiss inequality under an additional constraint when we have a non-negative a? So let me just remind you that this means I have to avoid this counterexample that I highlighted on the previous slide. And one idea is to constrain f to satisfy a differential equation. So what do I mean by this? I may ask for f to be a curl-free vector field or a suitable generalization of a curl-free vector field. So let me just explain to you what sort of differential equations I can take in place of curl. So one sufficient constraint is to impose this cocanceling condition. So this is like a generalization of the curl-free condition, but to other differential operators. And this was introduced by Jean van Schaffington back in 2013. So what does it state? It states that we need a condition on a vector field f and one other input. So this other input is going to be this differential operator L of d, and we're going to require that it is co-canceling. So I'm going to define co-canceling on the next slide because I want to tell you what the co-canceling condition is for f. So the condition is that there exists a co-canceling operator L of d, and L of d is going to annihilate f. So it's a two-part condition. First of all, I need the existence of this co-canceling differential operator, and second of all, I need that it's going to annihilate my vector field f. So I'd better tell you what a co-canceling differential operator is. So let's do that. So the co-canceling definition is just going to be the following. For a finite dimensional vector space, so I need two lines to essentially tell you what a differential operator is. So in other words, I need to tell you which vector spaces it maps between. I need to tell you what order it is, and I need to tell you how many variables I have. So once I've told you all of that, I can pick a representation for L of d, and that's just going to be this representation in terms of its action on the partials. So once I have this representation, I'm going to say that L is co-canceling if there exists a family of operators K alpha, one for every alpha, such that these K alphas act as a partial left inverse for L. So what I mean by that is that if you compute this sum, you're going to get back the identity. So this definition might seem like a bit of a mouthful, but I promise you that once you see it applied once, it's not going to be so bad. So let me just do that. This first point is just going to recall the key part of the definition, which was just that we had this family of operators K alpha that were a left inverse for L. So given these K alphas, we can construct a polynomial P of X such that L of d adjoint applied to P of X is the identity operator. So this P of X shouldn't be too mysterious. Let me just tell you what it is right now. So it's going to be K alpha adjoint with this polynomial. And what's special about this polynomial is that it's exactly equal to 1 when you hit it with the correct partial, and it's going to be 0 otherwise. So if you compute L of d adjoint P of X with this as your P of X, you're going to get exactly L alpha adjoint K alpha. And if you look at the adjoint of this formula, you're going to notice that this is exactly the identity. So how do we use this? We're going to use it in the following way. If I have a vector field f, I'm allowed to multiply it by the identity. I'm going to multiply it by this form of the identity. And now what's going to happen is that if I'm allowed to integrate by parts, this L of D adjoint is going to hit F. So I'm going to have this expression. Now, in particular, if I assumed that F is co-canceling, then note that this last term here is going to be 0. So what I'm essentially telling you is that co-canceling vector fields are going to be 0 a lot of the time. So let me just give you an example of a co-canceling operator. The simplest example I can think of is the gradient. So here L of D adjoint is going to be divergence, and the polynomial here should be x over n. So in this case, let's just note that the divergence of x over n is going to be 1, and 1 is the identity on our functions u. So now I've told you a definition. I should try and convince you that this definition is useful. So let me show you how we can use it. So if I constrain f in this way, so I impose the co-canceling condition, we obtain an unexpected family of Stein-Weiss inequalities. So let me state the precise theorem. Precisely, this is going to be, well, first of all, I need to suppose that my parameters satisfy the necessary conditions. If I additionally suppose, first of all, that A is non-negative, but strictly less than 1, and in addition, I suppose the co-canceling condition, so that means I need a differential operator L of D, and I need that L of D is co-canceling. Then if I impose that, I obtain the Stein-Weiss inequality for every f constrained by the co-canceling condition. So in other words, I obtain the Stein-Weiss inequality for every f which is annihilated by my co-canceling differential operator. So this is all well and good. If we reflect on this a second, we may be motivated to ask if this co-canceling condition is necessary. So perhaps this co-canceling condition was sufficient because it was very strong and essentially trivialized our problem. However, I'm going to say that De Napoli and Picon also thought about the necessity of this condition, and they can tell us the following. So they can tell us that if we have a non-zero f satisfying the annihilation condition, and we have the Stein-Weiss inequality at the endpoint a equals 0, then it must have been that L of D was co-canceling. So if you like, this second part of the theorem is telling us that the co-canceling constraint is necessary for the Stein-Weiss inequality at a equals 0. So what I'm telling you is that at a equals 0, this co-canceling definition I just gave you was an appropriate definition for this inequality. So now let's look at the other range of A. So we don't know if the co-canceling condition is necessary yet if A is strictly between 0 and 1. So let's ask if it is necessary. Now the short answer is going to be no. In my thesis, I proved the following theorem. So first of all, I'm going to require the necessary conditions. Then I'm going to ask if A is not an integer, then I'm going to obtain the Stein-Weiss inequality for every f satisfying the vanishing moment condition. So what is the vanishing moment condition? It's just going to be for every multi-index gamma less than or equal to the floor of A, the gammath moment of f is going to be 0. So how does this relate to the previous theorem? So when A is strictly between 0 and 1, I have my non-integer assumption. And in this case, the vanishing moment condition is just going to be a mean 0 condition. So I just want to remark that this mean 0 condition is weaker than the co-canceling condition. I'm not requiring some co-canceling differential operator L of D, and I'm not asking for a pointwise condition. I'm just checking that the mean of f is 0. So, so far I've told you that I'm able to weaken a theorem in a certain range. So if I've got a weaker hypothesis, that means that I must have made a gain in some other step of my analysis. So let me just highlight that for you now. So let me just remind you that I'm asking for LQ norms of the Rees potential. So I'm going to be analyzing this term. Obviously, I don't have time to go through it in detail, so I'm going to pick out one barrier and focus on that. So the one barrier I want to point out is that this kernel is not going to be integrable as x goes to infinity because this exponent is too big. So I'm just going to say that if I can somehow reduce this exponent, then by standard arguments, I can close my estimate. So let me tell you how to reduce this exponent. So we can reduce this exponent by Taylor expanding this kernel around the origin. So if we do that, we're going to get derivatives of x, and we're also going to get polynomials in y. So how many times do we need to Taylor expand? Well, I'm going to Taylor expand m times, and then I'm going to obtain a term of this form in the Taylor expansion. So this is just y to the m times x to the lambda minus n minus m, f of y, for some integer m, and I'm going to stop when I reach the floor of a. So then in this case, the exponent of the absolute value of x is going to become this number. Now, let me just tell you that I recognize this number. This number here is going to relate to the scaling condition. So let me point out that if m is less than a, so this is the case where a is not an integer, then I'm going to have that this number is going to be strictly less than minus n. And when I'm in this range, then I know that I'm going to be integrable as x goes to infinity. So that means I can close my argument with just the vanishing moment condition and this integrability criterion. So if you like, the moment condition comes in because I have some polynomial of y times f of y, and I know that this moment is going to be 0. So that's how I'm going to close the argument in the easy case. Now, something goes wrong when a is an integer, so let me point that out. If a is an integer, then m is exactly equal to a. And what does this number here become? From the scaling condition, I know this is going to be minus n. And minus n is going to be a critical exponent, which means I can't close my argument by just integrability concerns alone. So this means I need to do something different. So I want to talk about what happens in this case. So the simplest case for me to discuss when a is an integer is going to be the case a equals 1. So let me tell you what I know about the case a equals 1. So first of all, we know that the cocanceling condition is insufficient. So also in the work of Di Napoli and Picon, they have the following counterexample. So they can give you a divergence-free vector field such that the Stein-Weiss estimate fails. So what that means is that I need a slightly stronger form of cancellation to close my argument. So let me tell you a little bit about what I can do. I have to take f to be a very specific form. So what very specific form do I need for f? I need f to be d sim u. So what is d sim? If you haven't seen it, it's the matrix that's du plus du transpose. This is going to be a symmetric matrix, which is why we call this the symmetrized derivative. So if I have f of this very specific form, I note that there are going to be further cancellations. And in this case, I'm able to handle the borderline case by deriving this property. So I'm hiding quite a lot in this basically step, but what I'm just saying to you is that terms of this form are going to be basically 0 because of further cancellations of this dsim. So let me just tell you what's important in this basically. So first of all, I have to replace x to the minus n with a derivative of a Green's function for dsim. So you'll immediately tell me that I've changed the question, and that's true. This means I'm no longer proving a Stein-Weiss inequality. However, it's not so bad because I'm still able to prove a non-trivial power weight Sobolev inequality for dsim. So let me just show you this theorem on the next slide. So I'm also able to prove in dimension 2 if A, B, and Q satisfy the necessary conditions. And in addition, I assume that A is in this range, which includes the bad endpoint A equals 1. Then I can prove this Sobolev inequality. And this is a non-trivial Sobolev inequality because there are no L1 inequalities between the gradient of U and d sim U. So this is basically all I know about these problems. There are, of course, some open questions that relate to this field of work, so let me state them. So first of all, is it possible to prove the A equals 1 case for other differential operators A of D? So by this, I just mean in the previous theorem, can I replace dsim by another collection of differential operators? So this would need to be some sort of n-1 cancelling framework, I suspect. The next question I want to ask is it possible to prove a Caffarelli-Kohn-Nirenberg interpolation for other differential operators A of D? So let me just remind everyone that there are no inequalities between the gradient and AD. So if you want an interpolation inequality, you have to prove it by hand. And the last question I had was, is it possible to sharpen these LQ bounds to these Lorentz scales? And I think the answer is yes. There's some recent work by Bright, Chanchi, and Spector, but I haven't read it yet to see what else there can be done. So this is all I have time for. If you have any questions for me, please feel free to reach me at this email address. I also want to acknowledge the help and support that I received from my supervisor, Polam, and also the help and encouragement that I received from Andrew, Jan, Carlos, and Pierre. And above all, I want to thank you, the audience, for listening, and I hope you have a great day.